Okay, so we will start with measures of measures of variability. Okay, we have measures of variability for ungrouped data. Let's start with talking about variability for ungrouped data. What's variability? Variability is simply referring to the measure of dispersion of data in a given data set. So our concern now is we're trying to find out how spread your data in a given data set, whether they're closer to one another, they are clustered somewhere near the mean, whether they are far away from each other. Now, we will do or we'll have now measures of variability. It's called measures of variability or measures of dispersion. Still the same with measures of variability or other measure of central tendency. They have also formulas for measures of variability. We then would start with measure of variability for group data and group data rather. So for ungroup data, there are several measurements of, there are other measurements of variability, but our focus this afternoon is just how to solve the variance, standard deviation, skewness, and kurtosis. Okay, those are the things that we're concerned this afternoon. What I would like to introduce or at least begin with is let us start with I need you to understand that when it comes to measure variability, one measurement also that is used to measure spread of data, the quickest among measures of variability is range, where range is simply highest score minus lowest score. Now, highest score minus lowest score, that will give you now the range as to where the scores in a given data set is being spread out. If this is the lowest score, highest score, we know for a fact that the data is just distributed within this interval. Okay, that's called range. Quickest to measure, but it's not reliable because we do not, or range cannot merely describe the situation what's between these two scores, between the highest score and the lowest score. So knowing the variability or the dispersion of the data in between these scores, range can no longer explain to us. So what we need now is we need measurement that is going to describe the position, the situations of the scores in between. Okay, we will start with variance. Variance, we have our, I'll give you first our formula for measure of variability for group data or variance for sample. I'll focus more on sample, although the most of the formula or the terms just included in the formula between sample and population is just the notation used for population and sample. And then somehow they differ in terms of denominator, but let's focus more on the sample. Let's start with variance. Okay, our formula for variance is S squared, the summation of x minus x bar squared divided by n minus 1. This is for variance. Another formula also is S squared equals the summation of x squared minus the summation of x, then square outside, divided by n minus n times n minus 1. We have these two formula, variance, and then we have also our S, which is standard deviation, which is simply S equals the square root of S squared. The same here. S equals the square root of S squared. Now, our main concern here is standard deviation is just like the standard deviation or movement or the spread of data away from the center or away from the central tendency, specifically mean. So, you know, there are three measurements of central tendency, the mean, median, and mode. But this time, we actually look into the dispersion of data, how far they deviate away from the mean. So, our computation is in terms of standard deviation. But for us to find the standard deviation, we still need to get variance. Now, let's take a look at this example. Okay, we have this example. let us solve the variability. This example, if I'm going to read it to you, a time study analyst observed a packaging operation and collected the following time. So these are actually in terms of seconds required for operations to fill a box of a fixed volume box 11, 12, 15, 18, 13, 18, 16, 14, 12, and 17. Find the range and variance standard deviation. So we're going to solve for the variance for this example. First that we need to do is we have to solve this one or find in your formula, if you notice, if we will follow the first formula, what we need is the mean. Okay? We need to solve for the mean. Now, first, what is the mean? What is X bar for this data set? Who can give me the mean for this data set? I will no longer show the computation for the mean here because that was our activity or at least our lesson before. This time, I'm just asking you, or I would just like to ask, what is the mean of our data, or what's the mean of this data? Because that's needed in computing this one. So that is, what's your answer?
14.6, sir.
Okay, we have
14.6, sir.
14.6. Now let us solve for x minus x bar column, which is now, that is the difference of each score and the mean. So you have 11 minus x or 11 minus x bar. That is the first score minus the mean. Let us rearrange the score. This is 10 scores. Let's just arrange it in order so we can see actually the distance. But this is not necessarily the purpose I'm showing you this one is because I wanted you to see what I am going to explain later on. Now, if we're going to start, let's start computing the range because actually this exercise here demands for the range as well. What is the range of this data? The range is simply 11 or 18 minus 11. Our range is 11 or 18 minus 11 would give us 7. Our range is 7. Now, then the first thing I will do, like as we will continue this one, our x here, the individual score minus the mean. So we will have for 11 minus 14, is it 3.6, correct, right?
Negative 3.6, sir.
Negative, sir.
Yes. Then you have 2.6, negative 2.6, 1.6, negative 0.6, and then this is 0.4, right? And then 1.4 positive, 2.4, 3.4, and then 3.4. Now, the next thing that we will have, we have already this column. Before we'll apply the formula, let us just try to get the average of each score as they deviate away from the mean. Let's see what is the result. You try to add this column. We have the negative and then the positive below. What is the result? The answer here is 0. If we will try to solve it this way, we will consider the deviation of each course away from the mean. Considering that there is negative here and there is positive, the indication, once you get the summation of this one, the answer is 0. That's why we need to get x bar square. We need to square this one that is trying to remove the negative value. The negative here indicates that the score is below the mean. Okay? And it's also understood that if the mean is 14.6, which is somewhere here, between this line, above and below, they are symmetrical. They are, the value here below and above, they are alike. That's why once combine them, the other one is negative, the other one is the opposite side is positive. The combined form is 0. So therefore, we cannot compute for the variability. So what we need now is we need to find the square of each, the deviation of each scores away from the mean. So this is going to be 3.6 squared, that is 12.96, 2.6 squared, 6.76. This is already positive because we already squared it. 6.76, 1.6 squared, 2.56, and then 0.6 squared, that is 0.36. You have zero point 0.4 squared, that is 0.16. 1.4 squared, 1.96. 5.76. 3.4 squared, that is 11.56. And then 11 point. Okay, after we have this column, we have now the square deviation. We call this column as the square deviation of each score. So we know now that 2.56 is like that's the number of deviation. This score, let's say, ay, sorry, where is it? They're no longer aligned. This entry here is the square deviation of each scores away from the mean. Now, let us compute for our standard or variance first. Because the variance is basically, it is the deviation of the scores away from the mean, but it's squared form. So we get the summation of this column because remember our formula is s squared equals the summation of x minus x bar squared divided by n minus 1. So we need to get the column this one to have the entry for the summation of x minus x bar squared. We have 60.4. Okay, this is now the summation of the total of our square deviation of each scores away from the mean. So we have 60. Now to solve that, that is 60.4 divided by our n here is, what is our n? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 10 minus 1, we have 60.4 divided by 9. With 6.71. By the way, we will round our answer to the nearest hundreds. Please take note that we will round out values unless stated. It's always round up to the nearest hundreds. That is for convenience sake. Okay, because it's expected that there are numbers here are non-rational. Okay, or non-terminating decimal. So therefore, to make it for us to have an ease and writing the numbers, we are going to end with the closest hundreds place. So that is our variance. Meaning to say, the variance of the score away from the mean is 6.671. Now, the idea here is that to find the standard deviation of each score, take note this deviation here was the result as we squared each value away from the mean. Okay? We squared each because of this value. That is us trying to remove the negative, because if we're not going to remove the negative, we will add right away. We cannot solve any distance at all because it would result to 0. So what we did, we squared each, that is trying to eradicate or trying to remove the negative values such that we will get the summation value of 60.4. So now we are going to remove the squaring again. The squaring that we did here, we will remove that again by getting the square root of our s squared. With that saying, we are now solving for our s, which is the standard deviation. You have 2 point in 2 decimal places. Our standard deviation is 2.59. So it's like saying now, later when we are going to look for measures of other relative position, we would say that a score, one standard deviation of the score as it deviates away from the mean is equivalent to 2.55 as its values. For example, this is the mean, and then there is a score here. If this score deviates from the mean one standard deviation from this point going here, it means to say that that distance alone from the mean going to the first score, that is equivalent to 2.59. Whatever units that we're talking about here. If this is about seconds, so meaning to say, one packaging operation, a particular packaging operation, as it deviates away from the mean, one standard deviation, that is equivalent to 2.59 minutes. So this is the first formula. But let us find now the other formula. Our answer was 2.59. That is our standard deviation. The other formula, by the way, is using this formula. S squared equals the summation of x, that is the summation of x squared minus the summation of x and then divided by n times 10 minus 1. Now, this one, between these two formula, this is quite easy in the sense that this one here, we don't actually solve the mean separately. But you notice the formula here, there is mean, or the value of mean was embedded, but it wasn't directly solved as compared to the first example. The tendency of the first formula is that as we compute the mean separately and then we subtract all the scores away from the mean, the tendency is when your mean is with decimal, then you're going to deal with a lot of decimal values later on. But in this case here, we can go away with the decimals because we're not solving for the mean unless if the given itself is already in decimal. But if the given is integers, then at least using this one, there is no worry with dealing with decimal values because we can go away with the decimal values here. First is we need to get the square of each value. So we need to find x squared. What is our first x squared? That is 11 squared. That is 121, correct? The square of 11. And then the square of 12, what's the square of 144, 169, 225, 200. Okay, let's continue. Now we have the total, and in the same time, we need to get our total also here. What's the total here? It's 146. Okay, to solve for this one, we'll just simply substitute. Our n here is 10 times the summation of x squared, that's 2,192, minus the summation of x squared, which is, our x is, the summation of x, sorry, the formula here is not correct. This is outside. This is supposed to be like this, which is 146 squared divided by 10 times 10 minus 1, 6.71. And then the same way, s is simply the square root of s squared. So we have the square root of 6.71 would give us 2.59. So either way, we will still arrive with the same answer. So it's up to you now. Which do you think is easier, this method or the first example that we have? Somehow can skip or at least go away with the decimal values, because in this case, only if the given scores they're all integers, then at least all the way we will not be dealing with integers in the table, but rather only in the computation. But if we will use the mean, which will still arrive with the same answer, by the way, we would normally encounter like these values here. But if the mean is whole number, then there's no problem also using this one, because the value here will also be whole number. Okay? But either way, whether you use this method or the previous one, it's up to you. Guarantee that you must arrive or you will still arrive with the same answer. That's one thing that I can guarantee you with. So again, how do we interpret this one? It means to say that if we're going to describe it, example, if this is the mean, this value here is the mean, which is 14.6. Now this score is 14 away from 6. That's approximately 0.6 standard deviation. Meaning to say, once this value, 0.6 times this one, that is how far 14 here deviates away from the average, which is 14.6. That is actually our next discussion when we talk about measures of relative position. So if you're going to ask, how far is 11 away from the mean? So we don't simply count it how many scores away from it from the mean. There is what we call standard. The standard distance of this score away from this line here, which is the mean. That is basically this score with this standard deviation, or which is squared, which with its deviation 3.6 times the standard deviation. That is how far this score is away from the mean. I hope so that is clear to us. Now, the next that I would like us to solve is skewness of the data. In this case, or when in this measurement, when you talk about skewness of data set, if I'm going to put it in a diagram, remember there is what we call graph of a normal distribution. So whenever you make a graph of a normally distributed data, if it's normal, it will resemble a bell shape. That's why it's also called as the bell-shaped distribution. Now, in that bell-shaped distribution, you will understand that there is what we call skewness of the data. Skewness meaning to say whether if the data is normal, then its skewness It refers to the how long the tail of the distribution to the right or to the left. It's like this. If you have a data set in graph like this as normal distribution, that's the normal. But the skewness of a normal distribution, the tail here, this tail, and then this one, they are just equal. They are symmetrical or identical in that sense. But there are other ways also or tendency that your skewness could be like this. It's possible to have like this one, meaning to say the tail here on the left side is longer. And sometimes you will also encounter a graph like this. The tail on the other side is much longer. That is in diagram form. But there is also a computation in measuring the skewness of the data. Okay, let's have now the formula for the skewness of the data set. So when you say skewness of the data, we're now trying to figure out the tail of the distribution, whether is it longer tail on the right side or longer tail on the left side. Otherwise, if both tails are identical or equal, it means to say that our data is normal or normally distributed. Okay, it's the same with our formula for variance, that is skewness equals the summation of individual score minus the mean n minus 1, and then this is s cubed. This is only for sample because you notice this symbol that we're using here, that is sample mean. If this is new, that is already population mean. But if it's also mu, the denominator here is not n minus 1, but rather only n. That's normally the difference when we use population or sample in our computation. So it's exactly the same with how we computed the variance earlier, but this time our exponent is already in cube form. Okay, let's not investigate how we arrive with this formula. Let's just use the formula to find the skewness of this data. Let's see whether this data is skewed to the right or skewed to the left, meaning to say longer tail on the right side or longer tail on the left side. Or else they have the same length of tail left and right, so we have a normal distribution. Now let's find the skewness of the data. So I'll have to erase this one because I don't have enough space. So what we need now is we will just triple this, or we'll just triple our x minus bar. So which is x minus x bar cube. 3.6 cube, 3.6 raised to the power of 3. That's 46.66. 46.66. Now this time, you notice I'll just give you the instruction whenever in this column you will do rounding of values to 2 decimal places. I said earlier that rounding of values is only tolerable or tolerated when you are in the final answer. But for convenience sake in our discussion, I already rounded values here to 2 decimal places, so I will not write much values. Okay? So please, in your quiz, I'll also indicate when you will round the values in this side or in this part of your computation. Okay? So then next you have 2.6 to the power of 3, that is 17.57. Please do follow me. 17.57 as rounded to 2 decimal places. 1.6 to the power of 3. 4.1 into decimal places, and then 0.6 to the power of 3. Okay. 0.22, 0.22, 0.6, 0.06, 1.4 power of 3, 2.74, 13.82, 11.56 to the power of 1,544.81, 1,544.8, and then 1,544.8. Let's find the total. I already rounded to the nearest hundreds for convenience because I only have limited space. And also in your quiz, I also specify there when you're going to round this area to the nearest hundred. But our general ruling is that we will only round off decimal values to the nearest hundreds in the final answer. But in this case, for convenience sake and in our limited space here, I already rounded here to the nearest hundreds. It's 3,192.34. Do you have the same answer? 3,194.92.34. That is our the cube of the cube deviation, the deviation of each scores in cube form of each scores away from the mean. So this is going to be the value of this one. The numerator is 3,192.34 divided by this is 9 times our standard deviation earlier for this one is 2.59, right? Then let your calculator solve the skewness of the data. It should be 3.4 cube. You did not inform me that right away. It's only 39.30. 39.30. 155.34. It's 155.34. So this is 155.0.99. Do you have the answer? The skewness of this data is 0.99. But more or less, this value here of our skewness of the data, it pertains, you notice the value is 0.99. That is somewhere closer to positive 1. Take note, for the value of skewness, if the skewness value is positive, that means to say the data has a longer tail on the right side or on the positive side of the distribution. Meaning to say there are more scores that is away from the mean, or no, it so happened that there is a longer tail. Remember the diagram I earlier showed you? So this is somehow called skewed, or this data set is skewed to the right, skewed to the positive value. Okay, but if your skewness value here is negative, it means to say that, or sorry, this is negative, this is negative, 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 negative. Combine that one with the negative values. I almost, that's why I said something is off. So we have the negative 46.66 going down. Let's combine that. That's positive. So let us solve again. So we have a positive distribution. You notice it's very, very similar. It's very, very close to 0. That's why if this is a situation now, we can say that the distribution is almost normally distributed, because the skewness of a normal distributed data set, the skewness value is 0. Okay, this is very, very much close to 0. No wonder that this distribution of these scores here is almost normal. So in this case, by the way, skewness of the data set is also would help you identify or know whether the distribution is normal or not normal. Normally distributed or not normally distributed. Okay? So that's the situation or the scenario here. And also, just to give you an interpretation, skewness of the data, when you have greater than or equal to positive 1, meaning of this one is positively skewed, positively skewed. And then if you have less than or equal to negative 1, that is negatively skewed, negatively skewed. So meaning to say, if your skewness value is positive 1 and above or more, it means to say there is a longer tail in the right side of your distribution. So if you would try to remember or imagine the graph, if you have a positively skewed distribution, there is a longer tail on the right side of the distribution of that graph. But if it's negatively skewed, that is less than or equal to negative 1, that means that there is a longer tail also on the left side. Okay, lower than the mean. But if your skewness is 0, it means to say normal. The data is normally distributed. Now let us have the kurtosis. If the skewness is pertaining the spread of the tail of the distribution, kurtosis also is referring to the peakness of the distribution, whether too high or too low. That is already in terms of force. So kurtosis is simply equals the n, or the summation of n x minus x bar to the power of 4 divided by n times n minus That's n minus 1 times s to the power of 4. So we need to solve this value here for kurtosis. So you have 3.6 to the power of 4, 167.96, and then 2.6 to the power of 4, 45.7, 581.27. 570.35. Okay, this is 570.35 divided by 10 times 9 times 2.59 to the power of 4. We have 1.41. 1.41. Normally here, there is what we call the value for this one is 1.41. The interpretation for kurtosis, there are actually three types of kurtosis. The situation for kurtosis, we have the leptocortic, the mesocortic, and then the platycortic. Leptocortic curve, and then we have the mesocortic curve. I don't know, we have the platycortic. When you say leptocortic curve, if I'm going to put this in diagram, it appears to be like this. I mean to say there is the peak of your distribution is too high. And then when you say mesocortic, that is the peak of this distribution is somehow just average. And then the platycortic, you have a flat distribution. So it will actually play a long way. If your skewness is negative or negatively skewed, I mean, it's like this. Sometimes the distribution is normal. They have the same the distribution is normal. That the tail is identical or symmetric, but it doesn't determine that the data are the same because we can consider the peakness of the data, whether it's platycortic, leptocortic, or mesocortic data. Okay, so in this case, the kurtosis will just tell you now how peak the data set, or it's just simply referring to um, the height or the peakness of your distribution. So normally the value here is you have the same with the skewness. If it is positive, then you are somewhere near you are falling under leptocortic curve that is too high, having a peakness that is very high. And then if you have mesocortic, that's the average peakness. And then the platycortic, that is when your kurtosis is negative. So since this is positive, somehow this data set happens to be on the leptocortic. If the kurtosis is just 0 or within somewhere 0, that is somehow the data is normal distributed. Okay, that's where the distribution of data falls on the normal. So at least that's how we compute for the kurtosis, skewness, variance, and standard deviations for ungrouped data sets, and then at the same time sample size or sample distribution.